Hello, my name is Forbes. I'm going to be talking about how you can get type safety all the way from the database to the front end. Hopefully many of you have experienced the benefits of TypeScript and type safety in general already. It gives you a much greater confidence in releasing reliable code to your end users. And it helps enormously, I think, in productivity when it comes to, say, refactoring code. So I think overall, not only does it give us more reliable, safer code, but it also lets us work faster as developers. But there are a few problems that prevent us from achieving all of the benefits of this type safety. We get the most out of type safety when it's truly end-to-end, and there's nothing in the middle between our databases and servers and external services and our front-end code that breaks that chain of type safety. As soon as you have those breaks, errors start to creep in, and it becomes harder to refactor code with confidence. So where do those errors come from? Well, they come from places where our types that we've written down are lying to us. They equally come from where we've written any, but I think lies are a better way to describe these kind of situations. So this can happen where we've got database queries. This is perhaps the sort of silliest cause of unsafe or untyped code. Our databases are, for the most part, strongly typed. Postgres, MySQL, any kind of SQL database, almost across the board, has a strongly defined schema, and yet, on the whole, we don't have good tooling for saying what the type should be or detecting what the type should be when we run a query. And this can lead to code in, say, a Node.js code base having any's creep in anywhere we query the database. And if not any's, then maybe types that have been written by hand and may not actually match what the database returns in practice. Like I say, types lying. They also happen with APIs. It's often common to see cases where the API boundary introduces cases where we've guessed at the type, or we're just typing what we think it is, but we don't really know what our APIs return necessarily. And then third-party APIs are perhaps the worst offenders. You get third-party APIs will just change without warning sometimes. I've had an API where they changed the domain name without significant warning. How are we meant to deal with that as developers? Well, we can start to think about how we protect ourselves from these situations. Even if in the case of third-party APIs we can never truly prevent them, at least we can detect them early and address them as quickly as possible. So I'll start with the database queries and how we get types from our databases. I wrote a library called @databases, well, really a collection of libraries called @databases. And one of the things that this offers is a CLI for both Postgres and for MySQL, and others are coming, that will allow you to take your database schema and generate types from it. Once you've run that command, what you get is a whole series of files that have types like this in them that represent the types for your database tables and each of the columns within your database table. You can then use these when running queries, and this is still unsafe, right? So nothing here is connecting the select star from users to the fact that I've said that this is going to return an array of DB users. But the DB users query type was directly generated from the database, so at least if I change the database schema now, add new columns to the users table, or maybe remove a column from the users table, that type still updates to reflect that. So I'm not entirely just having a complete disconnect between the database and my types. There is some level of connection here. We've made things better. We haven't made things great. So the next level is a library that's part of @databases called pgtyped, @databases/pgtyped. That would let you take the generated types from the CLI, and it allows you to have a type-safe API to access your database and do basic to moderately complicated queries in a type-safe manner. For example, if we wanted to select all of the users that were created within the last hour, we could run this query and get just the IDs of those users And again, this is completely type safe now from our back-end application in Node.js all the way to our database. And over time, I expect this to expand to allow more complicated queries. And a future thing that I'm actually currently working on is an SQL parser that would allow this previous query with select star from users to also be truly automatically type safe. But while it's easy to imagine writing a parser for something as simple as select star from users, I want to support as much as I can the full gambit of queries that is supported by, say, Postgres or MySQL and so on. So it's going to take a little while to figure out how to handle all of those different cases. So okay, let's say that we've got our backend and maybe it's written in Node.js and it's got types all the way from the database. Maybe it's written in some other library or other language and we've figured out how to get the types from the database that way. We've still got to deal with our API layer. One option here is to use GraphQL. So if we've used GraphQL, we have a schema that's a well-defined, clear schema for our API, and we have clearly defined operations for our client. So we can generate types from the schema and the operations. One way to do this is using a library called GraphQL CodeGen. That gives you this kind of flow where you take in your schema on the left, you configure it, and it generates types on the right, in this case for the server, but you can also have it generate types for your client. And it'll generate, again, much like @databases does from your Postgres database, this does from your GraphQL schema and generates those types for you. An alternative, though, which gives you much more flexibility, is to generate those types yourself. So rather than relying on some library that will give you an off-the-shelf CLI to try and generate these types for you, you can go a level lower and use a few of the libraries. Like GraphQL offers a functions for parsing the schema and validating the schema, and Babel CodeFrame, which is part of the Babel compiler project, is this really useful tool for producing really well-formatted error messages. So if in the process of trying to generate your schema you find some invalid GraphQL, you can generate clear error messages using Babel CodeFrame. Once you've parsed the schema using GraphQL's built-in parser, you get back something that you can iterate over and just generate a string of TypeScript from if you need to. So in this case, this code is generating the TypeScript code for the types for our resolvers, for our GraphQL resolvers. You then need to just write that to disk, and I recommend a little utility to write a file if its value has changed, and then another utility to write TypeScript files and use Prettier to format those TypeScript files. So if you're generating code, I find the easiest way to generate TypeScript code usually is just to generate it by creating a string of TypeScript code, but then run it through Prettier, and then the output you'll get will look as if you've done a really nice, careful job of handcrafting that TypeScript code. Okay, so what if your internal API is not GraphQL, but let's say for now it is in Node.js? Well, next option is to use a shared types package of some sort. So we can use Yarn workspaces to great effect here to share code between our front end and our back end, and have a package for our shared types, a package for our front end, and a package for our back end. And then using Yarn workspaces, we can combine all of those and build all of them together. Our shared types package could define types for the request and the response for each of our API endpoints. And then we can create an endpoints type that lists all of our different endpoints and their respective types. So in this example, I've just added /API/auth and said that this is an endpoint that takes an auth request and returns an auth response. Having done that, I can add that as a dependency in both my front end and back end, and I can also add that reference in my tsconfig file so that TypeScript knows that this is a local package and knows where to find the actual source code. That'll help speed up the build process and just make the tooling a bit nicer. So having done that, I can create a function to build an API for a given path. So given a path, I can now extract the type from that endpoint type that we constructed This is now entirely a type-safe utility for creating a function that will then be type-safe and allow us to pass in some request and get some response from the backend. So to use that, we can just construct an auth API by simply saying make API and passing in that /API/auth endpoint. And if I mistyped that path, it wouldn't match any of the types in endpoints, and therefore I would get a type error on that line. Equally, if I now try and pass something that's the wrong type to this function, I'll get type errors because it knows what type that API endpoint now expects. So as we can see, when we hover over it, we can see that it knows that the auth is a function that takes an auth request and returns a promise for an auth response. So on the back end, we can do something similar. This time we want to make sure that the back end implements every single endpoint. So we can construct a type from our endpoints type that matches the type we would expect each of our implementations to have. So we're saying for each of the paths, we want an async function that takes the request for that path and returns a promise for the response for that path. And then in terms of implementing the endpoints, we simply have, for each of these endpoints, an async function that takes the request and returns the relevant response. Obviously, we might shift that async function into its own file if we were, once this grows beyond 1 or 2 endpoints. And then we can construct a router, say a Koa router, or this would equally work with Express or whatever library you wanted to use. And we can just loop over the paths and handlers in that object we just constructed to attach them to our router and simply pass in the request body and set the response body based on what that function returns. So this gives us type safety end-to-end now for an async REST-style API, providing that our backend and frontend are both written in TypeScript. What if we have an internal API, though, that's in some other language that's not in TypeScript? So our backend is no longer TypeScript. Well, one option, as we've already sort of seen, is to use GraphQL. So in most libraries, it's not inconvenient to expose a GraphQL API. So if this is an internal API, we can maybe have a conversation with the team that builds the backend and say, well, could you maybe expose your API as a GraphQL API? Because then we know we'll be able to generate great types for that GraphQL API on our client side. And probably whatever language they're using to write the backend in, they can generate nice types for their GraphQL API on the backend as well. But let's say that it's not convenient for it to be GraphQL for whatever reason. Maybe this isn't even a web API. Maybe this is like a procedure call of some sort. Maybe that just isn't sensible to expose as GraphQL. Well, maybe we can generate code in some other way. So I'm not going to go through this in a ton of detail because it's going to be different for every single language you might choose as a backend. But for every language, there's going to be a way to achieve this kind of thing, I think. So in this example, I'm generating types for a Rust API. And I'm using, most of this Rust code you don't need to worry about the details of. The point I wanted to raise, though, is I'm using a package called syn, S-Y-N, and I'm calling parsefile and giving it a file name. And I immediately get back, or giving it file content, rather, and I immediately get back a tree, a list of nodes representing the source code of that Rust file, which means that I can list through all of the structures and data types that are defined in that file, and I can just loop through them as relatively simple objects that can be understood. So I can then loop through those items and print each one out, and I would only really be interested in enums and structs for the purpose of printing out types for this. So I could print those out. If I'm printing an enum, for example, I can just generate some text that matches the TypeScript type structure, say an export enum of some name, and then print out each of the variants in turn, and then each of the variants I'm just printing the name equals the value. So I realized that was a lot of Rust code, and none of you are, well, most of you are probably not Rust developers. But the point I was trying to get across here is it's not actually a huge amount of code, and it's not hugely complex code. So if you do have a back-end team working in Rust, and you're sitting there as a front-end developer going, well, they haven't exposed any TypeScript types for their API, maybe sit down with them for an hour or two and see if you can write a script together that will generate TypeScript types from their API, because then you get that huge benefit of knowing that the types in your code on the front end that you're consuming exactly match the types of objects that they're returning from their back-end API. So let's say that maybe we're not talking about some API now. I just want to look at another kind of example of generating code. Again, this time we're back in TypeScript land, so you can all relax. There's no more Rust in this talk. The example I'm considering now is from a genuine bit of code in our application at Mavenoid, where we're dealing with translation keys. And we use a third-party service to manage those keys and translations. And what we get back is some JSON files, one for each language. And they look a bit like this. There's more keys in them. But broadly speaking, we have one of these JSON files for each language. And they each have the same keys and the appropriately translated values in them. Now, JSON is all well and good, but I'm writing in TypeScript. I want to be able to refer to these translations, these strings, in a way that I know is type safe, where I know that I'm not going to accidentally refer to a language that doesn't exist or a key that doesn't exist. So I want to have a file like this at somewhere in my code base that defines the type of a translation key, what is the key into these catalogs of translations, and also defines a type for my languages so that I'm only considering the languages that actually exist in my translations. So I didn't want to write this by hand. I obviously could if it was only a few lines, but as the number of keys grow, this is going to need to keep being updated. As the number of languages grow, this needs to keep being updated. If we remove a key or we remove a language, we need to make sure we update this, otherwise we lose type safety. And actually generating this file is pretty easy. We just need to read in the JSON for one of the languages, and that gives us a list of keys that we can print out as our list of translation keys. We can then list each of the files in the directory, and that gives us our list of languages that we can print out as that language type. And then finally, at the end, we can write out that types.ts file. And again, we can use Prettier to format this automatically for us so that we get kind of readable code out of this, even if maybe our kind of string concatenation, string building was a bit messy. And then just to demonstrate how this sort of thing could be used, now that we've got a type for language and a type for translation key, we could expose from this package a function that takes a language that we know will be EN or ES or whatever languages we add support for in the future, and returns a function that takes a translation key, which we know again will be hello world or talk title or whatever keys we add in the future, and returns the translated string. And this gets to be completely type safe. There's no chance of accidentally passing the wrong stuff and having this just not work at all, because we've got that type safety from end to end. Sometimes there's just nothing to generate types from. Sometimes all you have is some nice markdown files describing the API, maybe a nice website. Maybe you just have some emails back and forth. Once I got a Word document for an API, and I have no desire to try and build some script that parses the XML format embedded in a Word document and tries to, I don't know, do natural language processing to extract an API from it. I don't think that's going to get me anywhere. So we're left with, I think, the sort of only remaining option, which is runtime validation. And runtime validation can be worth doing even when you have generated types from some defined schema, because APIs change. Maybe you're lucky and you work at a company with perfect communication, like I do at Mavenoid, every team in perfect harmony, and you never have this problem. But I've also experienced companies where a team will make a change without realizing it's going to break your code, without realizing that you have something in production that already calls that API. And when that happens, you want to find out about it quickly and you want to find out about it with an error that makes it clear that it's coming from the value that's returned by that API, not some internal property X does not exist on null type of error. So that's where runtime validation can really save the day and really help you. So we'll come back to our internal API example from earlier. Let's say that we actually do want to enforce runtime validation as well as this shared types package here. And one of the reasons we might want to do this as well is because as this is perhaps a public API on the internet, even if we only intend it to be used internally by our application, there's nothing to stop a malicious attacker from crafting arbitrary JSON payloads that don't match our expected request type. And equally, in terms of the responses, maybe somewhere in the back end it reads from a MongoDB that doesn't have any database that doesn't have any type safety, or maybe we do some complicated SQL query that we haven't figured out a way to generate types for, and maybe we want to make absolutely certain that the responses we send to the front end are type safe. So anyway, we'll come back to this example now where we've got our authentication request and response, and we can use this funtypes package that I built, which generates, which allows you to create a runtime validation for TypeScript type. So the syntax you can see doesn't change a huge amount, or syntax changes a bit, but the kind of structure of this is very similar. And we can define these objects that have properties that are strings, numbers, booleans, etc., also all supported. And we'll get now runtime validation, but also static types as well out of this. So we can now change our endpoints so that rather than just the types, we can start off by providing endpoint schemas rather than just the endpoint. So these are at the top, our runtime validation, but at the bottom we use the static utility from funtypes that takes in our schema and produces a static type that is understood by TypeScript from that schema so that the two are always guaranteed to match and stay in sync. So now on our back end, we can keep everything else the same. Our front end doesn't need to change, and we can keep all of the rest of our back end the same, and just change this bit at the bottom where we create these, we link these handlers into our Koa or Express or whatever it is, router. We can extract the schema for each of the paths, and we can validate the request before we call the handler, and then validate the response before we return it to the user. Now, one of the things you may have noticed here, if you're looking very closely, is that the methods I'm using here are safe parse or parse and serialize, not assert valid or validate or anything like that. And the reason for this is that funtypes isn't just a data validation library, it's also a library for parsing and serializing data between different formats. And I think parsing and serialization make far more sense in most contexts than validation. So rather than taking in a value and answering the question of, is this valid, you take in a value and answer the question, can you convert this to something that's valid? And if so, what is that, that value? And one of the advantages of that is it lets us extend to types that perhaps can't be represented directly within JSON. So we might say we want to transfer a date between front end and back end. We can't transfer a date object as that object. We have to convert it to a string or a number or some other representation. So if we were purely validating, then all we could do is say, okay, we validate it, maybe that it is a date, but we lose that information because it's actually still a string. We lose the fact that we validated this as a valid date. We can't encode that in our type system. But by parsing instead, we can say, okay, when it's in its transit, when it's in that JSON format, it's a string. Having parsed it, now it's an actual date object. So funtypes comes with this companion package called funtypes schemas, and it implements all of these additional types, some of which are pure validation. So for example, base64 string just takes, is just a validation essentially that says, is this a string? And if it's a string, is it valid base64 encoded data? Like, does it contain only the characters that are allowed in base64 strings? But you can go one step further and use a parsed base64 string, and that says not only check that it's a base64 encoded string, but then decode that base64 encoded string back to the original un-base64 encoded string. And you can do a similar thing with, say, parsed date time string, where in the parsed format, it's a date object, but once you serialize it, it becomes an ISO 86401 string. And then this is also still doing validation, so we get that parsing and that validation as one single action, meaning that once we've parsed, we know we have valid data. I wanted to share with you a little library that I've come across recently that I think is really helpful when you're trying to enforce this type safety throughout, which is TS reset. And TS reset, one of the things that makes it relevant to what I'm talking about today is that it means that .json and json.parse will no longer return any, they'll return unknown. And what that does is it forces you to do this parsing, to do this runtime validation, or at least to explicitly do an unsafe cast into whatever type you may have generated for that API call, rather than the any just kind of transparently leaking its way into your code base without you noticing. So TS reset is not something you can use in a library because it's a global change to how TypeScript functions, but you can use it safely within your application. So if you're writing a front-end React application, not something like an SDK, then you can use TS reset to ensure that you are properly using JSON, properly validating anything where you're taking in unknown, possibly invalid JSON. It also causes .filter with Boolean to work as you would expect in terms of filtering out nulls, which can simplify quite a lot of code. And it also fixes some minor problems around array.includes and one or two other things that are also all nice to haves. So to use TS reset, all you have to do is install it and then import it somewhere within your code base, and then it'll start functioning right away. So it's a really nice, simple library to adopt. Okay, so let's come back to the beginning and where types lie in our code bases. So one of the examples that we talked about was database queries. And we said that the solution there is that you can generate types for your database queries using @databases. There are other libraries that also work for generating types from your database. I'd prefer you to use this one because I built it. But I would also rather that you use one of the other competing libraries than use nothing at all, because I like to use software that works, and I'm sure I will use software that's built by many of you at some point in my life. We also talked about internal APIs, both GraphQL and REST. And for GraphQL, we said that the best approach generally is to generate types from your GraphQL code. And for REST, you can share types between the front end and back end if both are written in TypeScript. And if they're not, you may be able to generate TypeScript types from types that are exposed by the back end, even if they're in some other language. And then we talked about third-party APIs, where really runtime validation is the only way to go. So, that's all I had to talk about today. My name's Forbes Lindsay. You can find me on Twitter. I'm not calling it X. And I'll continue to be on there for now. And you can find myself on there. Thank you.